Okay, last part of this section, 8.1 is alternative sources or renewable sources of energy. So this includes solar power, hydroelectric and wind. Έτσι, είπαμε για τα fossil fuels, είπαμε για τα nuclear, τώρα πάμε να δούμε λίγο τα τρία τελευταία κομμάτια που είναι renewable sources, solar, hydroelectric and wind. Starting with solar, we'll say the following, that we have two different kinds of application of solar power, of solar energy. One is what we call ηλιακοί θερμοσύφωνες, the collectors, heating panels, or solar panels. Okay, so this is one thing. What's the main idea behind this is that sunlight is used to heat water. How? By coming into contact with the water that circulates in a system like this. So the sunlight usually hits a black surface to absorb the sunlight easier, and the pipes in the system circulate the water, so this will heat the water. So this is what we use the solar energy for, the solar power for. So this is one application. So we have to distinguish this from the photovoltaic cells. Okay, so don't confuse one and the other. So this is two different things. One, ηλιακοί θερμοσύφωνες. Two, photovoltaic cells. And the idea behind the photovoltaic cells is that you use solar light, photons, directly to convert this light energy into electricity, the DC. So this is like similar to the photoelectric effect, but not quite. It's slightly different mechanism for those who have done the high level class. But anyway, so special materials like semiconductors are used to do this conversion directly. So two different things. One is one is used for heating water. The other one is used for generating electricity directly. There is no special formula that you need to know for this section. And then we come to advantages, disadvantages. These are basic common sense advantages, disadvantages. For example, these are renewable sources, so they're free, they're inexhaustible, they don't run out as long as the sun is there. They're clean, there's no pollution, there's no CO2 gas, no greenhouse gases, no radioactive disposable, etc., products. There are some disadvantages. Of course, they have to work only during the day. The efficiency is still low, although it's getting better. Maybe the initial costs are better, not so high anymore. And of course, it requires a large area. That's the main issue, and you have to have a large area. And it's also an issue for the environment. Okay. What kind of question do you expect here? Something like the following. The average intensity of solar radiation incident on Earth is 245 watts per square meter. We'll see why this number comes about, because initially we calculate them to about 1400 watts per square meter reaching the Earth from the sun, but then it has to go through the atmosphere. Some of it will be reflected, etc., etc. You have to distribute it throughout the globe. So this is the number that you actually get in the end, 245 watts per square meter. So we'll look at this later. In an area of photovoltaic cells, solar energy is converted into electrical energy with an efficiency of 20%. Estimate the area of photovoltaic cells needed to provide this electricity to your households or to whatever station you have. So This is the idea with the photovoltaic cells, that you have a large area, or some area, that you have covered with cells. Of course, you have some incident radiation from the sun. This is the input power. So every second, this is what, this is the intensity, the incoming intensity that reaches the ground. And remember, the intensity is power over area. Okay, so this is in what comes in from the ground, from the sun. And then you convert this to electricity, to output with 20% efficiency, and you need this to be the output, electrical power. So we need to find this area, how big this area should be, that I need to cover with photovoltaic cells. Okay. The incident power is, of course, I times A. So this is what is calculated here. What is suggested here is that the incident power is whatever area I have times the incident intensity. Now, of this, 20% will be converted to electricity. So this is 20% that I will get. Let's say of this P, the incident power, and then P out will be 20% of P in. And this has to be 2.5 kilowatts. Okay, so 20% or 0.20 times this incident power, this one, must be equal to 2.5 kilowatts or 2,500 watts. Then that's it. That's all you need to calculate the area, and it comes out to 51 square meters. So this is a typical exercise that you expect to have. Okay, the next one is hydroelectric power. So this is the power that's coming from the from the energy of water that you have stored in some height. So we're talking about gravitational potential energy. So you have a mass of water, big mass of water at a height h, and then you let it run down, and this kinetic energy will move the mechanical parts of the generator. So we start with mgh. This is my energy. And remember, we usually do not play with the mass, but we have to use the density. So the density, if you remember, the density of any material is mass over volume. So I will write the mass as density times volume. And then I will say, how fast is this energy converted? Well, it's mgh divided by time. This is power. Instead of the mass, I will say mass is density of water times the volume. The density of water is something that you should maybe be familiar with. 1,000. In SI units, it's 1,000 kilograms per cubic meter. So the mass is density times volume, GH, it remains as is, divided by time. And this thing here, we usually call it the volume flow rate. This is how many cubic meters per second flow of water. And we come up with this expression, which is not in the data booklet, but it's easy to derive because you just need to remember this is mgh over time, the power of this hydroelectric dam. And again, advantages, disadvantages, like the solar power, it's free, it's inexhaustible, it's clean, there's no exhaust gases, there's no radioactivity. Disadvantages, you need high initial cost, you need a dam, θες χρειάζεται ένα φράγμα εκεί πέρα. And this may imply changes to the environment. So it depends on location, whether you have this big reservoir of water. Very easy example here, just application of this expression. We're not going to do it. This one is important because they ask it relatively often. So I'll say this is a source for studying it. This is what is called the pumped storage system. And what it is that it's actually the other way around. It's the opposite of what you intend to do. Usually you want to use the height and the potential energy of this mass of water that runs down, it's converted to kinetic, and you get electricity, but then you need to push some water back into your reservoir. So you spend some electricity to pump, maybe αντλία, έτσι, pump the water back to the reservoir, give it some potential energy. And even though this is not efficient, this requires energy. So you spend electricity to do the opposite. So you say, why should I do this? This is only for when there is high demand. So when there is high demand, maybe the grid is not efficient, well, it's not capable of handling all the requests of power demand. So you need to use this storage that you have. And the last one, the last renewable power source that we will examine is wind, anemogenitries. And see, this is kinetic energy of air. So you see a Sankey diagram similar to what we saw for fossil fuels. This is the input, this is the output, so 30% efficiency. What does the rest go? Any kind of losses that you have in the blades due to turbulence. Some of the kinetic energy of the air is not totally converted to electricity, or does not stop friction in the mechanical parts, losses to the electricity grid, etc., etc. Here we do have a formula though. So let me scroll down and see what's happening. Okay, we said the energy is kinetic, so 1/2 mv squared. This is what it is. So assume that air comes with some kinetic energy. Air has mass, air has density. Again, density is mass over volume. And in this example, we say, look at the volume, which is like a cylinder that goes through the blades. The blades have a cylindrical cross-section, A area. So let's say in time t, the wind has a speed v, and in time t or delta t, it will go through a distance s, which is v times delta t. So what is the volume of this cylinder? The volume of this cylinder is the cross-sectional area A times the distance s, this side, which is v delta t. This is where it comes from. So now the mass in the kinetic energy, 1/2 mv squared, P is the speed. In the kinetic energy, this mass will be written in terms of the density and the volume. So the mass is rho times A times V times delta T, and then the speed squared. And the power is energy per unit time. So if I divide by this delta T, I will get the expression of the power for wind, for a wind generator. This is in the data booklet. This is the only formula in the data booklet for this section, for 81. And what's important is that you get a 3. You had square, you get another term for the speed, you get speed cubed. This is important because they will ask this. If the speed of the wind doubles, what happens to the power of the wind generator? It will be times 8. Advantages, disadvantages, like any renewable source, free, inexhaustible, clean. Disadvantages, similar, all of them, depends on wind condition. If there is no wind, and you don't get any energy, some noise, or aesthetic problems. People don't like γεννήτρες στη γειτονιά τους. That's it. This is 8.1. So the next section is 8.2. It's more physics, radiation, greenhouse effect.